All right, so we'll start with one linear inequalities graphing, and you have two of them. We only did one of these on Tuesday, so we'll do another one. So the first thing you want to do, we'll start with the red one, is get it in y equals mx plus b. So I add x to both sides, and I get 2y is less than or equal to x plus 8. Divide by 2. There is like a 1 in front of the x, so this is y is less than or equal to 1/2 x plus 4. Make sure you divide the 8 by 2 as well. So my slope here is 1/2. That would be up 1 to the right 2, and my y-intercept is 4. So the two things that are different on this with the graphing and inequality is you have to do the solid line if it's less than or equal to or greater than or equal to, and you have to do a dashed line if it's less than or greater than. So this one is greater than or equal to, so I'm going to do a solid line. I start at 4, and I go up 1 to the right 2. Solid line because it's less than or equal to. Again, depending on how you feel about it, you can kind of look at that and say, okay, I'm going to shade below because it's less than or equal to, but you can always plug in the 0, 0 point. So I'm going to plug the 0 into the top equation because that's easier. 0 is less than or equal to 8. That's yes, so I shade towards the 0, 0 point. Okay, I'm just going to put a little arrow right there because I don't know exactly where I'm shading yet for the whole thing. And then for my blue one, to get y by itself, I just have to subtract 3x. So I get y is greater than negative 3x plus 9. My slope is negative 3 over 1, which would be down 3 to the right 1. And my y-intercept is 9. This one is greater than, so it's going to be a dashed line. So I start at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I go down 1, 2, 3 to the right 1. It's a dashed line because it's greater than. Okay. And like this one, when it's like this shape, it's kind of hard to tell y is greater than, so I should shade above it. But this is where it's kind of hard to tell exactly where to shade. So I'm going to plug in 0, 0. Again, I like to plug it into the top one because you just get 0 on the left side. 0 is greater than 9. That is no. So I'm shading away. This would be towards 0, 0, so I shade away from 0, 0. So I need to be to the right of the blue line and below the red line. My answer would be right here. Any point in that shaded area would satisfy both equations. All right, so that's one with two inequalities on one line. What we need to do, we finished on Tuesday with one with 3, so we'll do that next. We'll actually do one with 4 today. All right. So this one, my red one, again, it's easier to put it in y equals mx plus b, so I subtract 2x from both sides, so I get y is greater than negative 2x plus 4. My slope would be negative 2 over 1. That would be down 2 to the right 1. And my y-intercept is 4. So 1, 2, 3, 4. So I start at 4. And I go down 2 to the right 1. This is greater than, so I'm going to do a dashed line because it's not equal to. It's greater than, so I should shade above, so I'm probably shading over here, but let's check it. We'll plug in 0, 0. So 2 times 0 plus 0 is greater than 4. 0 is greater than 4. That is no. So I shade away from 0, 0. So I shade above the red line, to the right of it. That whole like looking at it and guessing which side to shade only works if it's in y equals mx plus b. My blue line, to solve for y, I need to subtract x. So I get negative y is less than or equal to negative x plus 3. I do have a negative y. To get rid of the negative, I need to divide by negative 1. What does that do? Anybody? I flip the sign if I divide by -1. So this is -1 divided by -1. It would be 1x. 3 divided by -1 would be -3. So my slope is 1. That would be up 1 to the right 1. And my y-intercept is -3. So I start at -3 and I go up 1 to the right 1. This is a solid line because it's greater than or equal to. So I should shade above it, but we'll plug in 0, 0. 0 minus 0 is less than or equal to 3. 0 is less than or equal to 3. So I shade towards 0, 0. So I need to be above the blue line to the right of the red line. That would be... Oh, I forgot my other one. I forgot this is a 3. Forgot about this one down here. Y is greater than or equal to 1. That is a horizontal line. So I go to 1, and it's a solid line because it's greater than or equal to. And it's greater than or equal to, so I shade above. So I got to be above the purple line, to the right of the red line, and above the blue line. It is not always this intersection. Like yesterday, we landed on this intersection, or Tuesday, whatever day. So we are going to shade above the red, to the left of the blue, and to the right of the red. So just because they make a triangle right there doesn't mean that's going to be your answer. It is possible that it's going to be something different. We'll see more about that in a second. I'll talk about why that's happening in like real life situations. All right, so we did each of those on Tuesday. I just wanted to do another one to refresh. One of the harder parts about these we're going to do, and then one of these does become a test problem, but is when you have to write the inequality yourself from a word problem. So inequalities are more real life than equations a lot of times, because if I'm, here's a cargo ship and it has a limited amount it can carry, or cargo plane, I guess. You're developing a product. You can only manufacture so many products a week. Like, it's not an unlimited number, so you could do less than that. You just can't do more than that. So coming up with the inequality it has a lot of real life scenarios here. So a small cargo plane currently has 155 pounds of cargo on board. In addition, in boxes weighing 50 pounds each will be brought aboard. Suppose that the total weight of the cargo board must be at most P pounds. I always like to start with the at most because it just helps me. So at most P pounds, when you see at most, it's always less than or equal to. It cannot be more than P. This plane starts with 155, but we're going to add boxes that are 50 pounds each. So where it says each is usually a multiplication, because if I add one box, it's 50 pounds, 2 boxes, 100, 3 boxes, it's 150. So this should be the answer to this one, because like in the, one of the reasons they may do less than or equal to P pounds is because one plane may carry, 1 ton and another plane may carry 1.5 tons or whatever. So you have different planes that could carry different weights there. So you want to make that a variable. So some of these aren't too bad to start with. We'll start easy here. At Teresa's auto shop, it takes her 9 minutes to do an oil change and 15 minutes to do a tire change. Let X be the number of oil changes she does, Y be the tire changes. So I'm going to write that real quick here so I don't forget. X is oil, Y is tire. Using the values and variables given, write an inequality describing how many oil changes Teresa can do in less than an hour, which it nicely informs you that an hour is 60 minutes. Okay. So less than an hour. So I want to do less than an hour. Like I like to start there. That gives me what I'm focusing on there. If she oil changes, 9 for every oil change she does, and 15 for every tire change she does. So if I add those together, it has to be less than an hour. So 9x plus 15y is less than 60. All right, this one I actually think is the easiest one to do of all, but I don't know if it comes before or after that one. For his exercise day, Bob plans to run and swim some laps. Table below shows how long in minutes it takes him to run each lap and swim each lap. So let R be the runs and S be the swims. He wants to exercise at least 30 minutes. So at least 30 minutes would be greater than or equal to. So we already had this, but at most is less than at most is less than or equal to, at least is greater than or equal to, okay? Those are just some tricky words there. So it takes him 3 minutes to run a lap, so 3 minutes times how many ever laps he runs, plus 2 minutes how many ever laps he swims. So how many does he have to do at least 30 minutes of exercise? Those aren't bad because they usually end up being they look just like the chart that they have there. So 3R for run and 2 swim for the S. All right, here's the one that will probably pop up on the test that I changed it to. This one kind of puts together what we've been doing recently. Dante does a weekly exercise program consisting of cardiovascular work and weight training. Each week he exercises for at least 12 hours. So that's always the part that I like to write. It just helps me come up with it. He spends at most 10 hours cardiovascular work. At most 7 hours on weight training. Let X denote cardiovascular. So X is at most 10 hours for cardiovascular. Let Y denote time for weight training. Y at most 7 hours. Okay. Shade the region corresponding to all values X and Y that satisfy these requirements. There's one thing I just thought about, but I don't know if they do. All right, so we didn't come up with the top equation. X, that would be X plus Y, right? Because how much every time he does cardiovascular plus the weight training, he wants to be more than 12 or greater than or equal to 12. Change my colors on these a little bit so we can graph them. All right, so my blue one, I need to put into y equals mx plus b, so I subtract x from both sides, and I get y is greater than or equal to negative x plus 12. So my slope is negative 1 over 1. That would be down 1 to the right 1. And my y-intercept is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I start at 12 and then I go down 1 to the right 1. It is greater than or equal to, so I am going to do a solid line. My red one, x is less than or equal to 10. That is a vertical line. So if you forget, go here. It doesn't really make sense to do it this way. It's going to be a vertical line. It is going to be solid as well because it is less than or equal to. I swear I changed that purple. And then my last of the y is less than or equal to is going to be horizontal. So 1, 2, 3, 4, 5, 6, 7. And it's going to be solid as well. Oh, you know what we forgot to do? We forgot to shade. So for my x1 less than or equal to 10, I'm going to shade to the left because of smaller numbers. Y is less than or equal to 7, so I shade down. So I'm to the left of the red line and below the purple line. Let's go plug in 0, 0 to figure out where to shade on the blue line. 0 plus 0, is that greater than or equal to 12? And that is no. So I shade away from 0, 0. So I need to be above the blue line, below the purple line, to the left of the red line. That looks like it is going to be this little triangle right here. A lot of times on word problems, no, I'm not going to say that. So that would be my answer. Like he could exercise anywhere those amount of times and he would hit his 12-hour mark and be less than 10 hours and less than 7 hours for the types of training.
Could you show the word problem real quick, please?
Yeah. The one hesitation I had about this, and I don't know if we necessarily need it, is a lot of times on these problems, they put like x has to be greater than or equal to 0 and y has to be greater than or equal to 0. I got to go look at Alex to see which way they do it. The reason they do that is because I can't exercise negative minutes, right? Like we're talking about a real life problem here, so it's got to be greater than or equal to 0. So I'm pretty sure on this problem they like only give you like this quadrant right here to show that it has to be a positive number, right? You have to have positive amount of exercise, 0 or more. Like you can't have a negative amount of exercise. So like I don't know for sure if you have to put those. We will double check. But we will see a lot of that because when we're talking about real life scenarios, like you can't have negative in a lot of stuff. All right. Like I said, that problem is the one that I decided to put on the test. We may come back and do another one of those in a minute, but let's get to the next part real quick. They kind of tie right into that too. So linear programming. Linear programming is something that is used a lot on real life scenarios because it does help us like maximize profit or minimize cost. So what you do is you have these constraints, you have these different things. We'll build some inequalities in just a second. And you graph it, and then you plug it into what they call the objective function. Our objective here is maximize this P equals 3x plus 4y. So maybe it's $3 for the first product, $4 for the second product. How many of the first product do we need to sell versus how many of the second product we need to sell to maximize our product? And we have some constraints, which is like this x plus 5y is less than or equal to 5 because it's how much time does it take to manufacture each product, different things like that. So I went ahead and graphed these in Desmos so you didn't have to watch me type them in on my iPad. But you can use Desmos on these problems. I highly recommend you using Desmos on these problems. I thought Alex was going to give you the graphing calculator to do it. So just use Desmos on these problems. That's why I removed it from the test so you don't have to use Desmos. But we'll talk more about that in a minute. So what you look at is you graph all of these on Desmos. And you are going to have this picture here, and it's kind of confusing because it's got 4 different shadings, right? But we're looking at where these sections where the shadings intersect. So what we are looking at here is kind of look for the darkest amount shading. Okay, so we're looking where the blue, the gray, and the purple and the red intersect. It is this area right here, this polygon where they all intersect. And what we're going to do is we are going to look at where the lines intersect, the edges of each of these lines, or the corners, whatever you want to call them, the vertices of that polygon. So we look at those. So on Desmos, you can just click on it, and it will make the point pop up there. And those are our 4 numbers that we're going to plug into the objective function to see what's going to maximize our profit. Those 4 numbers are going to be our most likely scenario to maximize profit, okay? So we are going to take those 4 points, and we're going to plug them into each of the objective function there, the profit function, okay, and see which one maximizes it. So we are going to plug in a 0, 0. So 3 times 0 plus 4 times 0. The 0, 0 one never really maximizes profit because that means we're creating 0 products across the board, so you're going to make $0, right? On this next one, we plug a 3 in for my x and a 0 in for my y, so I get 9. The next one, we plug a 0 in for my x and a 5 in for my y, so we get 20. The next one, we plug a 3 in for my x and a 4 in for my y, so I get, 3 plus 16 is 19, okay? So the one that would actually maximize profit is if we made 0 of the first product and 5 of the second product, okay? But maybe this company really likes to make the first product. So if we just made 1 of the first product and 4 of the next product, we'd only lose $1 or whatever for 20 to 19. So might not maximize profit, but we get to have more variety. Okay. So you want to use Desmos on these. You can't really do it by hand because you have to have those intersection points. And to find those intersection points, you'd have to do a bunch of algebra. So plug it into Desmos and get those intersection points. And then once you get those intersection points, you can plug it back into that objective function and get your answer. So to do another one, I just want to do another one right here because this is minimize. when we graph these, so the reason you'd minimize in real life is like if you're looking at the cost of the product. How much does it cost to produce this? We want to minimize the cost and maximize the profit, right? So when we do this, the darkest area is actually this area right here, right? So my intersection, can I make that like thicker? Yeah, there we go. My intersection is actually, of the shading, is going to be this area up there. So it doesn't create a like polygon that we look at. But my intersection points of those, now I did that big line and you can't see them, but the intersection point for each of those should be able to easy see them. And those are our 3 points that we're going to plug in on this one. Okay. And like I said, you are definitely welcome to use Desmos. Use Desmos on these. Don't do it the other way because it'd take too long. All right, so those are my 3 points. So I'm plugging it in and I'm trying to minimize this one. So we are looking for the smallest number. So I plug in a 1.6 for my X and a 1.2 for my Y. I get what? 3.2 plus 6 is 9.2. And then I plug a 4 in for my X and a 0 in for my Y, and I get 8. And I plug a 0 in for my X and a 6 in for my Y, and I get, 30. Okay, so the one that would minimize the cost is the 8. It would be better if we produced all of the first product and none of the second product. That would keep our cost down. So like if we put the two problems together, since we're doing cost and profit, you'd have to kind of find the balance there of saying, okay, let's minimize cost but maximize profit. It's cheaper to do product one, but we make more money with product two, and you figure out the best numbers to work with there. So this is what people do. They're called quantitative analysis, and they go in and they figure out this stuff where people can maximize and profit, minimize cost. All right, so that is what linear programming is. So now we got to put it all together with the linear programming problem. So this time they're giving us a word problem. We have to come up with the inequality. Then we're going to use Desmos to graph it, and then we're going to plug it in to check it. Okay, so coming up with these are hard. They're very easy to mess up when you do it because our brains just kind of work a little bit differently. So we'll try to show you some tips and tricks here. A mining company owns 2 mines. These mines produce an ore that can be graded into 2 classes, regular and low grade. The company must produce at least 325 of the regular grade. So I'm going to go ahead and write 325, must produce at least, so at least 325. And 540 of the low grade per week. So greater than 540. The first mine produces 5 tons of the regular and 18 tons of the low, and the second mine produces 20 of the regular and 9 of the low. So you have 2 different things going here. You got the 2 mines, but you also got the 2 different types of ore that they produce. So in the first mine, it was 5 of the regular and 18 of the low. And then the second mine, it was, sorry. It was 20 of the regular and 9 of the low. Okay. So these are confusing because you got 2 different types of ores and 2 different mines, but you want to like write it out kind of like I have it, where you're figuring out the regular because we know that constraint's got to be more than 325 a week and the low's got to be more than 540 a week. The next sentence says the operating cost of the first mine is 16,000 per hour and the second mine is 12,000. So we are going, that's our cost objective function right here, 16,000 times how many over hours we do the first mine, 12,000 times how many over hours we do the second mine. The first mine can operate no more than 37 hours a week. So there's another constraint, no more than 7 hours. It also can't operate no more than 37, would be less than 37, but it also can't operate a negative amount. So this has to be between 0 and 37. The second mine can operate no more than 34 hours. So same thing, it cannot operate a negative amount, and it can't operate more than 34 hours a week. So how many hours per week should be to minimize the cost? Okay, so we go graph this in Desmos. We put those 4 graphs on there. You can see by this picture. All right, so looking at this picture, you go graph them all on Desmos. You find the spot that's shaded the most. So it is here to here to here to here. You look at the intersection points of each of those lines that are highlighted. You just click on it in Desmos and it'll pop up. And then we got to plug those all in. All right, so I already have a couple of them right here. 13 and 34, you plug the 13 into the X, you plug the 34 into the Y, and you get 616 out. So then we plug in 2510. So we plug a 16,000 times 25 plus 12,000 times 34. Get out the calculator. That's 400,000 plus 408,000. So that's 808,000. And this one you do 16,000 times 37 plus 12,000 times 7. So we're plugging these into the objective function that C equals 16,000 times 37 is 592 plus 12,000 times 7 is 84,000. 676. So we were trying to minimize, so we look for our smallest number. So my answer would be this one. It'd be best to do 13 hours of the first mine and 34 hours of the second mine. For the coffee problem, for a given week, Miguel's Coffee House has available 1,664 ounces of A grade. So that's how much they coffee can they use. So that would be less than or equal to 1664. And of the B grade, they have 1536. They're blended into 1 pound packages. For the economy blend, so we'll make that red. We need 5 ounces of the grade A and 8 ounces of the grade B. For the superior blend, make that blue. We need 8 ounces of A and 4 ounces of B. So again, you got two coffees and two types of coffee beans or whatever you're using. So you got to make sure you set it up right. Always base it on the constraints of each one, and then you can go from there. What's next? There is a $6 profit of each economy blend, so that's 6 of X plus $2 profit of superior. So assume they sell as many blends as it makes. How many packages of each should it make to maximize profit? So we're trying to maximize that equation. And again, they don't give this to you, but we know X has to be greater than or equal to 0 and Y has to be greater than or equal to 0 because you cannot make a negative amount of coffee. So we go plug this into Desmos. And again, we are looking at this intersection right here. And it's kind of the darkest area shaded on Desmos. And we want to use those points that are the vertices of that polygon right there to come to get our points. So then we take those points and we plug each of those in to the objective function, which is our maximizing profit, and we look for the biggest number. So when we use 192 of grade A and 0 grade B, we actually get our biggest number there.